We're going to calibrate the pH meter today. First, it obviously has to be on, as you can see. And be sure when not in use that your pH here is in distilled water. And especially when it's not in use, because we don't want our readings to be inaccurate. So, to calibrate it, first we go to the calibration menu in channel 1, because that's where this is plugged in. Then we take our pH meter out of our distilled water, gently clean it off since the electrode is very sensitive, and stick it into a non-buffer solution. Carefully too. This is of pH 7. So what we're going to do is we're going to hit calibrate now. We're going to put in our reading of 7 since that is known. And then we're going to keep it in there until the voltage reading up here becomes steady. Okay, it's about 1.67, 1.66 going back and forth, so we'll keep that. Now we have to remove it. We clean it off again. Carefully. Rinse it off into distilled water. Remove it. Wipe it off again, and we're going to stick it in our other solution, which is a non-pH of 4. So we put it in here. Which is the one of the sequence? And we hit pH 4 since it's known, and wait for the voltage to come steady again. Seems to have stopped moving around 2.42, so we'll keep that. Take it out. Carefully wipe it down. Stick it back into the distilled water. And we have calibrated our pH meter.
To find the pH in a solution, you take the solution, take the pH measuring tool, wipe it off, clean it, put it into the solution after it's been stirred, and let it sit until it levels out. And it has leveled out at 3.03 pH. Now, clean it again. Reactions containing solids and liquids that are heterogeneous. Therefore, the concentrations of the pure solids and liquids are not considered. An example of this would be a rock inside of a glass of H2O or water. The rock is not going to dissolve, and the water is not going to affect the rock. So that's an example.
Okay, I'm going to describe the difference between a weak and a strong acid. A strong acid is a molecule that completely dissociates, such as hydrogen chloride. When it is put into a solution of water, all of the chloride loses its hydrogen atoms, and it is just at that point of equilibrium in the water. It's just all dissociated. And say a weak acid, such as acetic acid, only partly dissociates. So when it's put into water, some will dissociate and lose their hydrogen, but most will not. And it will continue doing this until it reaches an equilibrium point. At that point, the amount of acetic acid dissociating is equal to the amount of acetic acid that's also reforming. That is, its conjugate bases and its lost hydrogen atom are reforming. And that is the point of equilibrium. Okay, I'm going to explain the KSP constant now. It is called the solubility constant, and literally because it is for the solubility of the ions in a solution with moles per liter. And with this number, you can calculate the number of grams per liter that the amount of these particular ions will turn soluble in a solution.